So thank you everyone to be here. Welcome to the ICARL seminar series. For those of you who are the first time here, this is a series of talks on autonomous agents. Reinforcement learning is one of our hottest topics. And today we're super excited because we have one speaker that has traveled all the way from New York to be with us here today, and is no other than Eugene Vinitsky, who is one of the, I would say, greatest examples of real world taking, like reinforcement learning taken to the real world with success. And he's also one of the persons that is pushing most effectively to have an ICARL community across the world with things like the ICARL conference that we're having in August this year for the first time. And yeah, as you can see, I'm super excited to have him here. Before starting, these seminars are sponsored by InstaDeep and Google DeepMind. Thanks to them, we will have some sushi afterwards. So for those of you that are in person, please stay. We'll have some networking with the speaker. For those of you online, feel free to make questions on the chat. I will read them to the speaker. So please feel free to interact. And without any further overview, Eugene, all yours.
All right, thank you so much for the really nice introduction. London is not that far from New York, so I'm really happy to be here. It's no further than California. I really appreciate you all coming out here in what I think is your summer term, and when I assume you have more exciting things to do. So thank you all so much for having me. Thank you to InstaDeep and DeepMind for sponsoring this event. Thank you to Borja for inviting me. So my name is, wait, actually in the back, can you hear me? Am I yelling loud enough? Awesome. Okay, so my name is Eugene Vinitsky. I am a new professor at NYU, where I'm part of the Civil and Urban Engineering Department, and also the C2 Smarter Center, which is a Tier 1 transportation center run by Con Osbay. And I'm going to be talking about our work that we've been doing in figuring out how to deploy RL agents at scale. In terms of kind of the talk structure, if you want to interrupt me, that's totally fine. I love questions during talks, so go for it. The other thing I should say is I was thinking a little bit about what kind of the philosophy of giving talks. And so this talk is going to be at a fairly high technical level, as in it's not going to have a lot of technical details. The idea is to, kind of provide an overview of what I think is exciting in this area rather than like teach you about a specific paper in general. So with no further ado, and my clicker has died. All right, well, we're fine. Oh, nothing's working. Cool. Okay, so kind of the overarching thing that I have been obsessed with since I started my PhD a while ago is like, how can we scalably build new human AI cooperative systems? So systems that operate in settings with humans in the loop or being involved in some fashion. Because I'm lazy, mostly in simulation, and without any real humans, because human tests don't scale, and I care a lot about being able to scale things up and do things in a way that is somewhat efficient. And there are two claims I'm going to try to make through this talk and hopefully convince you of, and if I do a good job. So the first claim is that given appropriate conditions, RL is a pretty scalable thing. It has all sorts of nice benefits and advantages. And in particular, I think we're starting to see the emergence of a pipeline that allows us to scale and deploy RL, given that certain conditions are satisfied. The second claim I'm going to try to make is that these conditions that I'm going to set out are not satisfied yet for multi-agent systems. So we don't have them. But I think there is a pretty scalable path to get there. And I'll talk a little bit about the work we've been trying to do to kind of get to that state. And I'm going to lean towards being slightly more controversial rather than less controversial, just because I think it's more fun. So, take what I say with the tiniest grain of salt. Okay, so going back to what I said about being deeply lazy, the path that I've been kind of pursuing for a while in terms of research is kind of trying to create kind of closed loop systems that are kind of recursively self-improving and trying to work on little different pieces of that in the hopes of fixing things. So we have kind of open-ended digital twins that have really complex actor behavior inside of them and correspond to really rich simulated worlds. We want to feed those into RL algorithms. And from the perspective of engineering, I think I've always pushed towards these things, trying to turn these RL algorithms into like black boxes that we don't have to think about, that are just a thing that you input a task specification and it spits you out a policy, and you don't want to be in the world of sitting around and really knowing the internal details of these things. Kind of, trying to bring RL closer to the world of like large scale linear algebra solvers, where nobody really knows how they work except for 5 people. Kind of those things work spit out, high capacity neural networks, figuring out some way to wrap them safely, and then hopefully then taking those agents that you build, inserting them back into the digital world that you've created, and creating an ever richer, more expanding digital world, which I sometimes call open-ended multi-agent learning, or if I'm feeling very lazy, I will call it project vacation, where I just set up this loop and then I go away and I come back and I have cool agents. Okay, so I want to talk about a first instantiation of this loop in an attempt to fix some of the pieces here. By talking about some work that we've done over the past 3 or 4 years as part of my PhD and as part of a much larger group working on this. I did not personally deploy 100 RL controlled cars, but 40 or so people did. So I want to tell you a little bit about this project, some of the lessons we learned from doing this project, and kind of the conditions I think that need to be satisfied for this to have worked, and for other projects with similar characteristics to work as well. So the goal here, and kind of an instantiation of this kind of closed loop simple system, is cooperative autonomous vehicles. So on the top left, we have an overhead view of a stop and go wave. So these are kind of fluctuations in traffic that you've almost certainly experienced if you've ever been inside of a car. They can be triggered by a real world event, like a very sharp lane change or an on-ramp merge that's very aggressive. They can also just trigger spontaneously near a critical density of traffic. So because of the way people drive, they can set off these shock waves. And until the density of traffic falls below a certain amount, they don't really dissipate. So they will just kind of persist and travel backwards through the traffic. And our goal is going to be to create a platoon of cooperative AVs that smooth this wave out. And the strategy is up to a point quite simple. So if you see the cars with the arrows above them, that's our platoon of 7 cars. And everywhere there's a pretty big gap, the car in front of that gap is a cruise controller whose behavior we're modifying. And the idea is quite intuitive. It's that when a wave smacks into one of those cars with the big gap, the car needs to slow down. But because of the gap kind of serves as a buffer, and the car behind it doesn't need to slow down quite as much. And so the wave kind of dissipates as it passes down the platoon. And this is from a small scale test we did in 2021 with 7 cars, where we kind of showed that we could put these cars on the road without causing any car crashes before we want to kind of scale to a 100 vehicle test. And so we're going to try to build these controllers using RL, and then we're going to deploy them into the world and hopefully smooth some waves. And this is part of the Circles project, which is a really large scale collaboration between a bunch of universities and industry partners. And so I just wanted to put that up there to shout out all the different folks who were involved at this in some way. Okay, so what does this pipeline look like in the context of this work? So we're going to build some kind of digital twin. We're going to feed those into policy gradient algorithms. It's going to spit out a neural network. We're going to wrap it in some analytic safety conditions, which we can do nicely for following a car in front of you in traffic, where you can compute explicitly controls that never crash. And then hopefully we're going to deploy it, collect some data, close the loop again, update our digital twin, and keep rolling forwards. So the conditions that allowed us to do this thing, the first condition is a fast simulator. So here is a micro simulation of the I-210 in Los Angeles. So it's a pretty big stretch of highway in Los Angeles. And you can see kind of the wave occurring in the simulator that I'm showing. It's kind of propagating backwards a bit. Within that, the red cars are our AVs. They're going to be attempting to smooth that wave. And as you can see, this simulator, this is just a tiny little stretch of it, has thousands of vehicles in it. And if we're controlling a small fraction of cars, even 2 to 5%, that is on order of 20 to 100 vehicles that are actual RL agents in the simulator. And And this is a microsimulator called Sumo. It's a really great project maintained by a lot of folks. And it is not, in fact, what we use in this project. And the reason is because it's not fast enough. So we're gonna do something else. This is just a nice visualization of this operating at scale. The second thing that I think you need to establish, and this is actually the reason why we didn't wind up using Sumo in this project, is that you need some way to build trust. You need a way to like prove to yourself that you're able to close the sim to real gap in some way. And just usually through some amount of domain expertise that tells you like, I have a really good sense of what the sim to real gap is. I see a clear path towards closing it. So this is over here we have an example trajectory from a real world drive. So this is a car driving through congestion in Nashville, Tennessee, which is where we actually deployed our controllers. And the thing that I want to point out to you, and the thing that we were never able to get working in these microsimulators, is the huge variability of the velocity. So you can see that you're going at 15 meters per second, down to 10 to 15 to 10 to 15, almost to a full stop, back to 15 several seconds later. It's really hard to get this type of behavior to emerge in like a traffic microsimulator. But if you collect real world data, it just emerges naturally. And so this is actually what we did in this project is we would go out and drive a car during congestion. So this is not a congested drive, but we drove during congestion. We would collect radar data from those drives. We had a GPS and an IMU on the car, and we could, store the trajectory of our leader, and we could store our trajectory. And we would drive it over this 14.5 kilometer stretch. And we took 9 hours of driving, and we then converted it into a really fast simulator that we then trust because it's kind of calibrated by default. And so what does that simulator look like? It looks kind of like this. So we take our trajectory from the roadway, we place it at the front of a platoon, and then we just replay that trajectory. And then behind that trajectory that we're just replaying from the road, we place a bunch of human drivers. And then periodically we place a red car, which corresponds to an AV car that's going to try to smooth the wave. And when you do that, you get something that like very much kind of reflects what the trajectories looked like in the world. So this kind of like accordion-like behavior. It's sped up a little bit, so it's like a little more severe than it should be. But we could look at the simulator and be like, yeah, that looks right. That looks mostly right. So our AVs are going to try to smooth things and make things good for the human drivers behind them. And on occasion, you'll actually see a car pop in and out, and that corresponds to kind of a lane changing model. Though I should warn that the lane changing model does not have mass conservation. Okay, and this is kind of presaging something I'm going to try to say later. What model do we actually use for the human drivers in that simulator? So we used a popular model. It's called the intelligent driver model. It's kind of the thing that runs in a lot of microsimulators. And the important thing about the intelligent driver model is that it's wave propagating. So rather than the human drivers diminishing the wave, which would kind of defeat the purpose of the whole thing, it kind of amplifies the size of the wave. And it also has a lot of arbitrary hyperparameters that you can tune to ensure that it's actually wave propagating. And when you do that, and you build out the sim that we were showing you before, you get a time-space diagram that looks like this. And the way you read a time-space diagram is you have time on the x-axis and position on the y-axis, and 0 is the origin of one of those vehicles you're replaying. And every line here is actually a trajectory of a car. So there's 200 cars there, so they're kind of smushed together, so you don't see them as individual lines. But every line here is a car. And then black is slow. So you can see the waves that occur as these downward sloping black lines, indicating that we are actually constructing waves in this mini simulator. Okay. And the third thing that we had to do that I think is really, really important in deploying an RL project is doing really careful operational design domains. So having somebody come in and say, okay, I know something about the world that is very hard to stick into a simulator. I'm going to basically babysit your model and make sure that it does the right thing. And the way that this showed up in our project in particular is we have kind of a lane changing model that we don't really trust a lot. It's okay, but we know it doesn't do mass conservation correctly. So it's possible. So basically the way the lane changing model works is when there's a big gap cars will appear into that gap. They'll just like pop in with some probability. And they also have some probability of disappearing. And what this allows the RL controller to do is it allows it to really play with the lane changing model in some ways that we're not comfortable with. So for example, it can cause the wave to collapse, then a bunch of cars will disappear, and then it'll drive for a long time with many fewer cars than there used to be. It'll just do weird things like that. So like our careful ODD here is a domain knowledge reward, where our reward function is some combination of penalizing energy cost, right? We want to minimize energy consumption or maximize miles per gallon or kilometers per gallon, plus some penalty on creating excessive gaps. So if the car creates a gigantic gap in traffic or it squishes too close to the car in front of it, it's penalized for that. And that kind of prevents the controller from going into domains where we're not comfortable with our model, where we're not certain that it's doing the right thing. And similarly, even after doing that, we still had to do this like later domain knowledge injection, where sometimes we would get results that looked anomalously good, and we just had to sit down and watch them and say, that doesn't look like the behavior that we would want a controller to have. So we take these things, we take our simulator, we take our like method of closing this into real gap, and we take our careful ODD, and then we, run the RL loop, get the thing going. And because we try to be the good kind of ML person, we spent a huge amount of time trying to build kind of explicit controllers for this task. So like PID type controllers, like other analytic controllers. And so at the top in red, we have the human baseline run over like 10 held out trajectories. So instead of any car being an AV, every car is one of our human drivers. And there we get a miles per gallon of about 38 miles per gallon. In green, we have a bunch of model-based controllers that we spent a long time building. And in blue, we have our RL controllers after about 12 or so hours of training. And so they're pretty high in the fuel economy. They're kind of the best thing in fuel economy. And so that's the thing we wound up deploying or actually put onto the cars. And just to kind of calibrate as to what the kind of strategy that emerges from this process is. So on the left, you can see that figure I was showing you earlier, that space diagram. And then on the right, you can kind of see the same thing, but with these little white lines that have appeared. And that corresponds to the vehicles opening up these gaps that are going to smooth the waves out. And you can see that the earlier waves are kind of smeared out rather than being quite so sharp. And that's really good for energy because the energy model is quadratic in the acceleration. And so when you kind of bring the overall scale of the accelerations down, that corresponds to really large changes in energy consumption. Okay, so we have our controller and we took that controller and through a ton of effort from different folks from Vanderbilt, they outfitted 100 cars with a Comma AI Panda and a Raspberry Pi that was executing the controllers. Here they're just shown lined up in a parking lot, but we would just kind of place them all in a continuous stream onto the highway and then bring them back and then place them back onto the highway. And we ran that for 5 days on the I-24. And just as a shout out, the actual doing the RL piece of this was really spearheaded by Kathy Jang, Nathan Lischla, and Adit Shah. So want to give them credit where it's due. So we put our controllers onto 100 of these cars and we drove them around for 5 days from early morning to about the afternoon when congestion tended to disappear. And while I talk about that, I just want to shout out one kind of benefit of automation that I hadn't really realized until we did this, or one benefit of the RL loop that I hadn't really realized until we did this. Or this would be true for any optimization-based controller. And it's that it was very easy to adjust new models. So we were working on this project for about 2.5 years. And about 2 months before the deployment, we learned a very scary thing, which was we did not have the ability to tell how far away the car in front of us was. We thought it was on the CAN bus. It wasn't on the CAN bus. We don't know where it is. It's on some other part of the car that we didn't know about. And so instead of knowing how far the car in front of us was, we had a binary signal indicating whether there was a car 80 meters in front of us. And so we had to use that to try to, that combined with a bunch of like density data, like how dense the traffic was that we were buying from a company called INRIX, to kind of infer how far the car in front of us was. And then on top of that, we also thought that we were going to be able to do acceleration-based control. So like actually output accelerations and decelerations. And instead, it turned out the only thing we could do was flip a toggle that indicated how much the cruise controller wanted to close the gap. So we had 3 settings, 1, 2, or 3. We didn't entirely know what they meant because you can't, car companies will not give you a model of their cruise controller. So we had to like kind of build a model of the cruise controller as well. But the nice thing was like, we made those changes, we changed them in our simulator, we ran the RL loop, and then 12 hours later, we had a controller that was working again. And that was a huge relief. So I just want to point out this like wonderful benefit of optimization-based controls. Okay, so for measurement, we have, there's this amazing data set called I-24 Motion, which consists of 300 overhead cameras on 4 miles of highway in Nashville, Tennessee. It's like, you know, tens of thousands of hours of driving data. And so we could take individual trajectories and just follow them along the highway, which allows us to measure like the miles per gallon of a particular car very carefully. So if you want a giant data set of human driving, really recommend looking at that. And okay, so results. First of all, so we have this graph over here that's kind of indicating our results in sim, and split into 2 portions. It's split into a low-speed data set and a high-speed data set. And the reason for that is that these waves mostly occur below 18 meters per second. And so if you kind of smush them together, you don't really see the actual benefit. And the way to read this is going from left to right. We have the AV, or the cruise controller. We have the car behind it, the car behind that, and so on and so forth. And what you can see is this like really nice thing that we weren't certain would happen, which is that there's a benefit for the AV, and there's the largest benefit for the AV. And that's because it's both wave smoothing, but it's also optimizing its fuel model. And as you go further down, everybody in the platoon behind the AV is also benefiting, with those benefits diminishing as the wave kind of disappears. And so this kind of answers a question that we used to get a lot, which is like, why would anybody turn this on if you put this into the cruise controller of their car? And the answer is, it benefits you, it benefits everyone around you, which is kind of just a win. Okay, and then in terms of real roadway success, we are still in the process of analyzing that because it's a really hard off-policy estimation problem, because suppose you turn it on and there's no congestion. Well, it's possible that you just did a really good job and there's no congestion, or there was no congestion in the first place. So these kind of 5 days like help us to kind of reduce some of that uncertainty, and it's also just a lot of data to process. But so what we settled on temporarily is like I think a qualitative indicator of success. And what we do is we look at the cars behind the AV. And so you have the AV and then the cars downstream of it. And you do that because you can only influence the cars behind you. And as you move away from the AV, your fuel consumption goes up. So if you're close to the AV, your fuel consumption is low. And as you move away, it gets higher and higher. And so it's kind of a preliminary indicator that like in the local vicinity of the AV, it's doing some kind of traffic smoothing and, you know, getting some pretty serious fuel benefits for the cars around it. Okay, so getting into the second part of the talk, the takeaway is we think we've seen some success, but it's like very limited by sim capability. So we had to collect data to like build trust. We had to insert yes, question. Yeah.
To improve traffic management, that it has a bigger gap to accelerate.
You mean the AV has a larger gap to accelerate into? Well, the cars behind them don't have a bigger gap to accelerate into. because they will just bunch up like humans do, right? It's only the AV that has this anomalously large gap. Yeah, good question. Okay, so
online they also ask you what's the fixed penetration rate of these tests?
so the penetration rate fluctuated between like 2 and 5%, depending on where you were locally, because we have 100 cars and they're kind of spread out through the roadway in ways that are hard to predict. So we had 100 cars, you know, order of there's maybe somewhere between 2,000 and 8,000 cars on the road. So, you know, not a particular exact fixed penetration rate, but a low penetration. Okay, so we don't have a trusted lane change model, so we have to like do this kind of babysitting through domain knowledge injection of the reward function. And this is the thing that makes me the saddest. We have to do real world tests to tell if we're making progress. You know, this is not necessarily the world that I want to live in. And this is going to be like the real thing that I think is bottlenecking like multi-agent learning in general, is that you have to do a real world test to tell. You don't have a proxy measure that you can optimize. Okay, so going back and trying to re-summarize, some ingredients for working RL. First of all, you have a fast simulator. I think, yeah, I guess what I'm trying to say is if you have these ingredients, I think you have like everything you need for like a working RL deployment. You have fast simulator. You have some way to build trust between yourself and the simulator. And then you have a curated ODD. So you have a way of like setting up some guardrails around your agent that you are confident about.
I was going to ask a question about with the fast sim, which is like the important thing. Is that a compute problem or is that with data problem? Where do we set the fast sim?
I mean, the fast sim is because right now the set of algorithms that like work really well and robustly, like kind of like a black box thing, you can close your eyes and hit run on it, are algorithms that are extremely computationally inefficient. So you can get really good results with them, but you have to throw a lot of samples at them. Does that answer your question, or was it a different question?
We're bound by the
we're
IQ as opposed to the compute and data.
Yeah, we're bound by we're algorithm bound here. And a curated ODD. And I think if you look at the stuff that's like, well, if you look at our stuff, right, we got our fast sim, we have a way to build trust through collecting data, and our curated ODD is kind of telling the car to avoid large gaps. And I think the same thing is true if you kind of look at like other things that are starting to work really well. So like quadrupeds are like, people are building really nice algorithms, really nice behaviors in them through RL. And the things that they've built there that aren't necessarily the case in other places where people try to apply RL is they have these wildly fast simulators like Isaac Jim. They have picked a robotic platform that is like very trustworthy. It's got 4 legs. So, you know, there's like some robustness built into it. And then, you know, people will really carefully curate, you know, kind of curricula into the environment, and they'll only try to use them in settings where, you know, they can function pretty safely. And I think the same thing is kind of true for like some cool results in drones. So like drones are starting to work pretty well. And I think the reason for that is drone dynamics are really fast. You can simulate them incredibly quickly. It turns out that, you know, for closing the sim to real gap, you can just collect like a little bit of data and like fit a tiny neural network that fits the residuals of your dynamics and then stick that into your simulator. And then, you know, people are trying to use them in spaces where, you know, we kind of think that they can behave pretty robustly and sensibly, like going through waypoints and things like that. Okay,
hey, Eugene.
But I think that for multi-agent cooperation, which is the thing that I'm really excited about, like big multi-agent sims that help us learn something about the real world or design new behaviors or new ways of acting, we only have one of these 3 components. So we have very fast simulators. So if you look at Jack's MARL and things like that, they are incredibly fast simulators. But we have no way to build trust. We have no way of saying like, okay, I think that the human models in our simulator are pretty good. I think the results in them are something that I expect to transfer. And we also don't know how to say like apply domain knowledge to say something like, here's a domain where I think things will work pretty well, where I like have pretty low uncertainty about what the possible behaviors could be. And so until we fix these, I think we're going to be like pretty stuck. So basically, I think large scale multi-agent cooperative learning is trust bottlenecks or eval bottlenecked, depending on how you want to say it. And so I'm going to spend the latter half of my talk talking about the work we've been doing to try to like fix this like trust bottleneck portion and build like really good models of human behavior that we can then stick into a sim, optimize against, and then deploy. But to set some context, I want to talk about the ways that people try to fix the sim right now. So the problem of this like lack of trust or lack of ODD is that we don't have really good actors that we can stick into a simulator and just optimize against them, right? So we can't just like design a new controller that operates with a fixed model of human behavior, does a good job against it, and then we feel ready to deploy it into the world. And the way that we build simulated actors right now is we either use a rule-based heuristic. So somebody sits down and they write like a parametric model of how people should act, and then they stick that into their simulator. And that has some pretty serious limitations. So particularly in the space of driving sims, if you've ever used something like Carla or Waymax, the rule-based actors will like deadlock or smash into each other all the time. So it's pretty common in Carla to like get a bunch of cars drive up into an intersection. They all deadlock, don't move for the next 1,000 seconds. The simulator times out. Another option that is super, super popular is to replay human logs. So you collect a bunch of data in the world, and then you put that data on rails. So basically it just like follows along the trajectory that was collected in the real world, but in a non-reactive way. It is the case that sometimes people will build a little bit of reactivity on top of that. So if you cut in front of that vehicle on rails, it'll stop. But if you do that, RL agents will abuse them like crazy. They will just take advantage of whatever rule you've put in there. And then they will learn to drive it in a not robust way. And the thing that's really popular right now is imitation learning, where you collect a bunch of data and you learn a model through like behavior cloning or some other IL method. And if this if this image is any indicator of what I think the problem with that is, we'll talk about that. Okay. So this kind of imitation learning approach is kind of built on an analogy from supervised learning. And the idea of supervised learning, like the thing that has like kind of worked so far, is that we take this gigantic set of diverse data collected from the internet, either through like huge amount of text, huge amount of images. We feed that into some big model, doing some kind of supervised objective. And at the end, we get a robust agent, you know, your ChatGPT or your humanoid that picks up eggs or makes coffee or something like that. And I think where this breaks down, particularly in the driving and in multi-agent domains, is first of all, most of your data just looks like this for hours. Like 90% of your data has no interactions in it. And problem two, and this is where I'm going to pick on a company for a hot second, is that I don't think it really seems to be working as well as people would hope. So recently, Tesla announced that they had driven 1 billion miles across all of their vehicles with their like Autopilot enabled, which is really, really exciting. Except after having driven 1 billion miles, they have an intervention somewhere on the order of every 100 miles, which I actually think is like an optimistic upper bound for how often somebody has to intervene and take over. This is collected from like a community site where people like log when a disengagement happened. So I think these people are probably a little optimistic and maybe don't log everything. And so the issue here is we have this huge amount of data, more data than a company like Waymo has ever collected, like probably 10 to 100 times more. And when you feed it through this imitation learning pipeline, you get a thing that is not all that robust. And I think kind of like a similar thing is true for ChatGPT. And the reason this is a problem, like there are certainly domains where having an intervention every 100 miles is amazing. If you are building a lawnmower robot and every 100 miles of its driving, you need to come out and fix it, that's fine. But if you want to use these agents as part of a simulator, then what happens is, and your simulator runs at like 1 million frames per second, like some of these really fast simulators, then that's a collision, multiple collisions every second. And as a consequence, you're generating tons and tons of data that you then have to go in and label and ask, who was the source of this collision? Was it my imitation learn model, or was it the agent that I'm trying to learn inside of the simulator? So this is like not even close to the collision rate that we need, even in our simulated agents.
It's a question on line from Brian. I will step in what you answered. Is there an implicit assumption in building trust that we have some notion of sufficient understanding of the domain problem, example, low enough uncertainty or even risk? I think you answered this in the early before going into the ways to address the overarching issues, but feel free to respond of this if I'm mistaken.
Okay, is there an implicit assumption in building trust that we have some notion of sufficient understanding of the domain? Yes, that's basically what building trust means. There's a human there that we trust. They're a domain expert. Okay, so because I am a man of one hammer, I'm going to tell you that RL is the solution to this problem. In particular, I'm going to talk about some work, an archive paper that we just put out with my student, Daphne Cornelise, about kind of using large-scale self-play to try to build like more robust agents. And we're not there yet, but I think there's like signs of life that I think are very exciting. And so in contrast to this kind of imitation learning approach, I would say that there's one way that we know how to build superhuman agents, or even like human level agents. And that way is large-scale self-play. So like in multi-agent games, you put two agents against each other, you run some like black box RL algorithm, you get your superhuman Go agent, you get a human level Stratego agent, and so on and so forth. So we have this amazing tool for solving zero-sum in cooperative games, and we're going to try to bring that to the driving domain. So this is a visualization of a simulator we built called Nocturne, built with some folks at FAIR. The goal for each of the agents is to reach that little circle. That's their corresponding color. These are trajectories taken from the Waymo motion dataset. And then on the right, we have their partially observed view. So the idea is we're kind of trying to recreate the view of what a human would actually be able to see, right? So they can't see through other cars. And that's important because it gives us the ability to do things like reason about the fact that another agent might not see you, and that maybe you should make eye contact with them to confirm that you guys see each other. And we're going to just try to run self-play at scale. And each agent is going to know its goal, but it's not going to know the goals or perceptions of the other agents. So there's some inherent uncertainty in this problem. If we do this and we like run this at scale and we kind of do all the like good RL things, then we get an agent that is extremely good on crash rate. It almost never crashes, but it drives like this. And it gets worse. Yay! I made it to my goal. Hooray! And the problem is that in outside of two-player zero-sum games, you can run self-play to get human like or human plus level policies, agents that like never collide. But there are many equilibria, and they're not compatible. So as the like most like naive variant of this, like there's no reason for self-play to prefer one side of the road to the other. So your self-play run will either converge on driving on the right-hand side of the road, like, you know, America, or on the left side of the road. And there's no a priori reason to assume that. And you can run and train your agents. They'll learn to drive on the left-hand side of the road. You'll deploy them in America. Terrible things will happen. So what we've been trying to do and figure out is how we can like go from like some high-level specification of a game, stick it into a self-play algorithm, and then use either demonstrations or human preferences to kind of shape the resultant equilibrium that we get out so that it satisfies some desiderata. So for example, that game objective could be like maximizing diversity, and then you specify some preferences over like which agent you want to pick out from that diverse pool. Or in the case of the specific game we're doing here, that objective is to reach all goals. So we're going to spawn goals all over the map. We're going to ask our agents to reach them, and then we're going to try to shape the resultant equilibria so that it, you know, looks a little bit more like human driving. And the way we're going to do this is we're going to do an IL regularized goal reaching game. So if, you know, this thing here represents the space of all goal reaching policies, and this here is the particular policy that humans play, where they capably reach goals, but do it in a particular way. Well, if we have like a small amount of data from human driving, then maybe we can assert that all these other ways of reaching goals are unlikely under the data. And so, yeah, driving is some combination of capable goal reaching and preferences, and this instantiation of the game will teach our agents to be capable. And then we'll figure out preferences from data. Let's skip this. Okay, there's some like, I think possibly underappreciated work that says that this is maybe a good idea, which is this work on no press diplomacy that came out of Facebook AI research from Anton Baxen. And the cool thing that happened in multiplayer diplomacy is that if you run self-play in multiplayer diplomacy, you get agents that look really good. But if you take one of those agents and then you play it with a bunch of human players, the human players wreck that agent. And the reason for that is diplomacy is a many-player game, and it has multiple incompatible equilibria. So you have to actually play like the agents you're playing with. But they threw in like a particular like data regularized self-play problem, and then they got a human level agent. So they like took a little bit of imitation data, they built an imitation policy, they used a particular regularization objective, and then immediately the agent that emerged from self-play there was transferable to play with humans. And I think that this is a like very underexplored and exciting hypothesis, and that's why we're exploring it. So what we do, we call it HRPPO. These are some wonderful graphics that Daphne made. And the idea is that we're just going to combine like a normal like RL objective with a small regularizer term to stay close to some behavior clone policy. That's it. And in particular, we very purposely make our reward like have no shaping inside of it. So the only reward is to reach your goal. So anything on top of that that emerges, you know, which side of the road you stay on, whether you stay lane centered, whether you stop at stop signs, is all going to be from the imitation policy. And okay, some quick training details. So we train, we take some data from the Waymo Motion data set. We train a behavior clone model that has a 50% goal reaching rate, which so it's a bad policy. It's like very bad at reaching its goals. And we do that using 30 minutes of data. And the only reason it's so bad is because we couldn't figure out how to make it better. So we would love for someone to give us a better IL model, or we'll figure it out eventually. And then we run it over like 200 different scenes taken from the Waymo Motion data set. And then we test it on 10,000 held scenes. And if we do that, we get the following set of results that I think are, we're not there yet. You know, we're not at 0% collision rate. This car does not drive for 50,000 miles without colliding, but I think it's moving in the right direction. So there's a couple ways that we kind of measure whether this procedure is giving us the thing that we want. The first is the result of the thing that emerges from self-play should kind of look like the human data. So we measure that in two ways. First of all, you know, how close do we match an expert trajectory given conditioned on the fact that we know the goal? So like this kind of here is a visualization of how ADE works. Like we're trying to get to this goal, and at each point we're measuring the distance from the expert trajectory. And there we see a pretty small trade-off. So as we like increase the regularization towards 100% PPO, we go from this like 50% goal reaching rate of our BC policy kind of up to like 95 or so percent, while still maintaining a pretty like similar trajectory to the experts. And an important thing to note there is that we actually like that goal rate percentage is still like ticking up. We just had to shut it down because we ran out of compute. And, you know, along another metric, which is kind of like differences in actions between the expert trajectory, because it's possible to follow the same trajectory while wobbling along it really rapidly. We still see that the actions are like quite similar. So in terms of like the difference in the steering angle taken along the trajectories, it's like basically identical to the behavior clone policy for like any small regularization parameter.
I have a couple of questions.
Yes.
For instance, you're mentioning how far these landmarks, like how far you are from the human preferences that you're giving.
It's how big of a regularization parameter.
Yeah, like my question will be rather, is that that policy that you're trying to be similar with the one you're distilling from the behavioral cloning or from some training data that you have?
We're not measuring distance to the policy. We're actually measuring distance to like ground truth trajectories.
Oh,
Like, yeah.
then the question will be like, how well this generalizes to when places where you don't have a ground truth policy to check.
Well, I mean, we're measuring this ground truth distance on the test set. So that's, I mean, that's really all we can do,
Oh,
right?
And the second question will be, have sensitivities to have you were saying that you would like, but this is how good the behavioral coding could get. Have you tested how sensitivities to having a better or a worse behavioral coding?
Yeah, so we desperately wanted to generate scaling curves where we like increase the BC policy and we see correspondingly how the RL policy increases. So we could see like, maybe if our BC policy was at 60%, we'd actually be at 100%. Because we can look at what the BC policy is telling us to do at some states, and it is very frequently yelling at us, crash into a wall as fast as you can. And so we think that if we can make a BC policy that does not constantly tell us to crash into a wall, we will probably crash into walls less often. But like, that's very doable, right? Like if you look at Waymo papers, like their BC policy is like right up there. So we just have to figure out how to do it. The other measure, we want to check that our agents are like closed loop effective in self-play. So if we, make every agent in the simulator a copy of our agent, are they capable of getting to their goals without colliding with each other? And in self-play, we do see that. So we go from this 50% BC policy to about a 95% goal reaching rate, both for the regularized PPO and for the normal PPO. And then 3, like log replay. So this is kind of another imperfect proxy measure for compatibility with human drivers. But we take all the expert trajectories and we just like run them in a non-reactive way. So these is like a complete holdout test set. We've never trained with agents that don't react to us. We've only trained with copies of ourselves. And there we see kind of a 15% improvement over baseline PPO and a much larger improvement with respect to the goal rate for our agents, which is in orange. And this 15% improvement kind of understates things a little bit because, as I mentioned before, almost all driving is straight line driving. And if you actually look at like interactive scenes where we have some kind of proxy measure of interactivity, which is like how often do the agents' paths cross each other, then the difference between like normal PPO and our regularized PPO is much larger. It's about a 40% difference in collision rate. So we're like flat no matter how interactive the scene is, whereas normal baseline RL agents just get worse and worse and worse as the scene becomes more interactive. I think it's also, kind of worth seeing what these look like qualitatively. So on the backwards, on the left, we have the original scene, and on the right, we have kind of what our agents actually look like now. So super boring, which is exactly what you want to see. And you can also kind of see this in like more intricate scenes. So, okay, on the right, we have pure self-play, and the cars are like not really good at like navigating these highly interactive roundabouts. And on the right, there's just like, you can see that white car is like just like smoothly waiting to enter the roundabout, which I think is super nice. And you can also kind of see this in log replay. Like, so log replay here, the red car is a car we're controlling. The gray cars are cars that are just kind of replaying their trajectories. And you can see that, PPO like does not wait for them. They are expecting it to wait at the stop sign. Whereas, our agents just like wait just like a little bit longer to establish right of way. Anyways, so last thing, as I mentioned, we ran into scaling issues at some point where we were training these agents for 2 days and we could see that the curves were going up continually, but the cluster would kick us off after 2 days. So we've been working on scaling this up. These are 2 master students in my group, Sam Kazampani and Arav Pandya. And they have been working on trying to fix this for us. So as we know, multi-agent training is very expensive. If we look at we did some kind of cost estimates of what different agents took in terms of actual compute dollars, and so OpenAI 5 is order of millions of dollars, Poet is order of hundreds of thousands of dollars, and so on, AlphaStar and so on. These are probably underestimates. They almost certainly were more expensive than that. And here, based on an informal survey, is what we think an academic compute budget is. So a little inaccessible. And this is what we think an academic compute budget looks like when you switch to the world of batched simulators written in JAX. So they really unlock a lot of magic. And we have been trying to do the same thing for driving. So we've been building a simulator called GPU Drive that should be out in the next week or 2. which is a 2.5D multi-agent driving simulator that runs somewhere between 750,000 steps per second and 3.5 million steps per second. The difference is we have these padding agents that are currently in the simulator that are just like fake agents to make the number of agents in the sims match. And once we figure out how to get rid of those, we go up to 3.5 million. And if we don't get rid of those, we're at about 750,000. But we do know how to get rid of them. It comes with LiDAR, which is pretty annoying to write in JAX. I mean, you can do it, but it's annoying. It's built atop this great engine some folks at Stanford released called the Madrona engine, which lets you write your simulator entirely in C++, which then gets transpiled to CUDA. And if you think that writing your simulator in C++ is easy, then you get batching for free. Yeah, so just to kind of like wrap up and take some time for questions, I want to thank a huge number of collaborators, particularly the Circles advising group, who made it so that instead of having to figure out how to put our controllers on 100 cars, helped us just focus on writing the controls. A huge number of different organizations that I've worked with over the duration of some of this work, and a huge number of collaborators. And of course, I got to thank the Emerge Lab, which is our new group at NYU, and our PhD students and master students, and Franklin, you and Tiffany, who are missing. Have to end by plugging our RL conference. So we have a new RL conference, August 9th to 12th in Amherst. There's some great speakers. If you're wondering, what is David Silver up to? What's he doing? Well, you can come and find out. And we have a number of accepted workshops. If you missed the deadline, I didn't submit a paper. And yeah, with that, I just want to thank you for attending my talk. It's late in the evening, and I'll take any questions if you have them.
That's your way of doing this regularization video. It's like doing inverse MARL, including the actual reward, and then using the like a normal video.
I think it isn't, and the reason that it isn't the same as inverse RL is I don't have to write down the reward terms, and I don't know what the right reward. If I'm doing inverse RL, I want to learn the coefficients of some reward parametrization, and I don't know what reward parametrization I should have. What is the set of terms that go into the reward function for human driving? Are there dyadic terms? Are there terms that factor in interactions between three agents? Is it speed? And so you wind up with this gigantic reward function. And we don't have to do that. But I do think I'm not certain what is the equivalence between IRL and IL. Yeah.
Hey, Eugene. It's
Question in the back.
Oh, we have hands up too.
To repeat the question, just to be sure I got it right, because it's kind of quiet from there. Would the simulators be improved if the agents could communicate with each other? Well, we want our simulators to reflect reality in some way, right? We're trying to build models of human behavior, not a fully autonomous world. And so humans can only coordinate implicitly through actions, blinker signals and turning their head. So they do have the ability to communicate through action, but not through explicit signals. If we were interested in simulating a fully AV world, then I think it would be super interesting to add in more interesting ways of communicating. And I think that's a super fascinating problem that we're just not touching here yet. There's a question over there. Yeah.
Just one, thanks for your talk. Seems to me that you have the reward, which you define, getting to the destination is 1, the rest is 0. But then do you assume, I think you also have some sort of underlying model regarding the movement of vehicles, which is the digital twin doing for you, is it true?
Yeah, I mean, so we do have a dynamics model for the vehicles,
Right.
Which is just a kinematic bicycle model, which is what people use.
So in that sense, that that model would not be a concern of your enforcement learning agents regarding avoiding collisions and other things.
No, I mean, they're learning to avoid collisions in a model-free way. So they're learning to plan through that model. And I mean, in practice, I also think the model is super important. We know how to make cars that follow waypoints for pretty arbitrary models. So like the physics is not the real challenge here.
Then will you tell us a little bit about the possible actions that your agent is going to be?
Yeah, so it's a bicycle model, so they can steer the wheel and they can hit the brakes, that they can hit the accel and decel, and they can turn their heads. Though in this work, we actually don't let them turn their heads. We just make the field of view wider.
And then the actions by the agent would be reflected through the simulation according to.
Yeah, they go through the dynamics model. Yeah. If you don't do that, then you wind up with cars that like violate physics a lot of the time. Yeah. There's a question behind him.
I just want to ask you about the wave sprucing project. Yeah, you need to collect the real driver data because it's hard to simulate because like you drop to start and come to 15 speed, something like that. But you want to do everything in simulated work. Then like how do you use those collected data to use those techniques you introduce later to like introduce agent behaving like human?
Yeah, so so this latter work is actually like in some sense inspired by the challenges we ran into in that first project, right? Like being really frustrated with insufficiencies of the human models in micro simulators. It's like at some point we want to go back and take these agents that we're building and make them the base agents in that simulator. And then if we do things right, they should produce waves kind of like humans do. But we haven't done that yet. If that was
Actually the wave sprucing model, which what kind of model do you?
Yeah. We were using this like intelligent driver model that people is like a common thing used in the transportation community.
Is it how you use those actual driver model in that, or you just like is the kind of future work?
So we have not used our current drivers in that simulator yet. Yeah.
Have you tried residual reinforcement learning, or how does it compare to your regularized?
So when we say residual reinforcement learning, you mean I have a base controller and then I do RL on top of the base controller?
First you do imitation learning and then you learn apology, which is the difference between like you optimize that.
Well, yeah, I mean, I think that like the IL policy is so bad that like if we do residual reinforcement learning, you get like a little speed up from you first of all, you get a little boost in sample complexity. And then like that's a reasonable question because I think that will kind of force us. I don't know. I think that might work. I haven't tried it. Yeah.
Okay, so I think it's good moment to stop now. So thank you for all the questions. Before we go into the networking time, just for you to know, our next session will be on the 1st of May. We'll have Jacob Bruce from DeepMind to present as an example of the Genie paper. That's the one where they're able to generate 2D games with agents that are able to execute the actions that you prompt to them. And apart from that, we have also the reading group weekly going where we discuss works like Eugene has presented here today. So if you want more consultation to everything that is happening here, please reach us out any of the organizations here or by email. With all that, thank you very much.
Thank you all so much for attending.
Yeah.